Okay, maybe we can get started. So last time we talked about generalities about Poisson manifolds and Poisson structures. So let me just remind you of the general setup. So I just want to sit somewhere so I don't get this reflection on my screen. So the first thing is that the concept of directional derivatives can be extended by the notion of Lie derivative with respect to a vector field. So it's a directional derivative where the direction changes at different points. Okay, so this leads to these operators of differentiation, Lx, with respect to a vector field on a domain. And then we realized that the Lie derivative gives a structure of a Lie algebra on all the vector fields of a domain in Rn, or more generally a manifold. So you can then take the commutator of two vector fields, the commutator being defined as the vector field that corresponds to the commutator in the operator sense of two Lie derivatives, Lx, Ly minus Ly, Lx. Okay? And then we realized that this commutator can be lifted back to the space of functions on the domain. So you can now obtain a Lie bracket on the space of functions. But for this to make sense, or rather be canonical, you need to identify, or rather you need to construct vector fields from functions, or more precisely from derivatives of functions in a canonical fashion. And this basically means you have to identify the tangent space to the domain and its dual in a canonical way. But there's no sort of way to do this without any other structure, but one can choose a bilinear form on the tangent space and do this. And when we do this, if we do this with respect to a non-degenerate skew-symmetric bilinear form, we obtain a certain Lie bracket on the space of functions that's given by first order partials but multiplied as such. So in principle, it's this bracket which is known as the Poisson bracket. And this is the lift, this is the sort of pullback of the Lie bracket on vector fields. Okay, so this is what we understood. And then because of the specific form of, or rather the explicit formula that we got, or say the standard skew-symmetric, like a nonlinear, the standard symplectic form on the domain, we can see that this Poisson bracket, it satisfies the Lie bracket properties plus an extra property, which is the Leibniz rule. Okay, so this we checked. All right, this is like elementary, right? And what I wanted to show you is how to obtain an important example of a Poisson structure, which means a bracket on the space of functions, in the case where U is the dual of a Lie algebra, okay, for any Lie algebra. All right, so this is what I want to show you right now. But maybe before that, I remind you that if you have a map, what is the more like if you what is the like remind you what is the morphism between manifolds? The morphism between manifolds is just a differentiable map. And now we say if the two manifolds, or say the two domains, are equipped with Poisson brackets, then we say the map or the morphism is a map of Poisson manifolds if it maps the Poisson structures to each other. So more precisely, maybe I go on the next slide. And so here is a remark. So for two open domains, or more generally manifolds, say U and V, that are equipped with Poisson brackets. Say brackets of U and brackets of V. A map, a smooth map like f, that goes from U to V is called a Poisson map. If given two functions, say f and g, from V to R, well, we can compose these functions with f, this capital F, and we obtain functions on U, and therefore we can compute their Poisson bracket with respect to the bracket on U, which means we get a function from U to R. And we would like this to be the same as the function obtained by first doing the Poisson bracket with respect to V and then composing with F. Okay, so this is what we call a Poisson map. All right, just preserving the structure, mapping one structure to the other. All right, any questions so far? All is good? All right. All right, so now let's come back to this Lie algebra, or rather dual of Lie algebra Poisson structure. So let's consider, so this is an important example. So the G be any Lie algebra. So it's a real Lie algebra, okay? Like Lie algebra over R, we think about it as Lie algebra over R. And we consider G star to be the dual of G, which means all linear maps from G to R. That's a vector space as well, okay? And we know that the dual of the dual is canonical isomorphic to the vector space itself, so we know this isomorphism. So now, I would like to define a certain Poisson bracket on C of G star. Or I'm sorry, C infinity of G star. So G star is a vector space, so it's an open domain in itself, and we want to define a Poisson bracket of G star, okay? Which incorporates the Lie algebra structure. So the idea is the following. So if I take two functions f1 and f2, smooth functions from G star to R. So what we do is we look at the derivative of these functions. So these derivatives, so this df1, say, at any point. So where are the points coming from? The points are coming from the domain, which means like in G star. So it's alpha will be in G star. So this d f1 alpha, well, we should think about it as a linear map from G star to R. Okay? So this is a linear map from G star to R. And what linear map is it? It's just at any point, it just does the directional derivative more precisely. So df1 alpha at beta, it is just the usual limit that defines the derivative, right? It's the limit of f1 alpha plus t beta minus f1 alpha divided by t. Okay, just the derivative, okay? But then it will be linear in beta. Okay? Just this is the directional derivative in the direction of beta, so it will be linear in the direction. All right? And so this means that we get this linear map, and therefore df1 alpha is something in R star, which is canonical isomorphic. Okay? So this is canonical. So now what I do is I define f1, f2, this Poisson bracket, at the point alpha. So remember, again, this should be a function on G star. So I should evaluate at some alpha. So alpha coming from G star. All right? So I define this to be the value of the functional alpha at the commutator of df1 alpha and df2 alpha. So again, remember that df1 alpha and df2 alpha are elements of G, right? Because they're in G star, so they're in G. Therefore, this commutator makes sense. This is with respect to the Lie bracket of G. And when I do this Lie bracket, I get an element of the Lie algebra G, and alpha is in G star, so I can evaluate it, right? So maybe if you want a more sort of a traditional way of writing this, it would be alpha of this bracket. Okay? Is it clear? Right? All right, so now the claim is that, so we show, or rather we claim, we show that we actually got a Poisson bracket. Okay, so we have to check that we actually got a Poisson bracket. It's a Lie algebra bracket, it's a Lie bracket, and it satisfies the Leibniz condition. So in order to do this, let's first compute an explicit formula for this bracket in some sense. So what we can do is we can try to use coordinates and write this bracket in coordinates. How do we do this? Well, we can take a basis for the Lie algebra and the basis for the dual. So we take a basis. The x1 to xn for G, and the dual basis like C1 to N for G star. So this means that Ci xj is delta ij, which sometimes I might use this notation for the pairing between the Xi's and xj's. Okay, that's just a dual basis. This is linear algebra. Okay. All right. So now, what is the derivative? What is the derivative of a function at a point? So the derivative in these coordinates can be given as the vector whose components are the directions in terms of the sort of canonical basis that I've chosen. Not the canonical basis, but the basis that I have chosen. Okay, so this means that this is really sigma df dxi of alpha times xi. So here the point is that the directional derivative in the direction of xi would be this number, or rather xi would be this number. Or more precisely, if I do df alpha of xi, I'm expecting df dxi, right? This is the ith component of the gradient vector, and it is just this number, right? But now, what linear combination of the xi's I should write so that if I apply xi to this, I get this? Well, the coefficient of xi should be this number, so that when I apply some cj, the only one that's non-vanishing is when I equals j, right? Okay. So this formula dictates that this has to be the vector for the derivative. Okay, because this, upon evaluation at xi, I should get the coefficient df dxi. And then by the property of the dual basis, this vector over here does satisfy this property. Okay? So let's say follows from. Okay, so now we have this kind of a explicit way of writing this df. And now, if I want to do df1, df2. So now the good thing about this formula is that, in fact, I already used the duality between G double star and G. I wrote this on the right-hand side as an element of G. Okay? So this is the key point, is that I just wrote it as an element of G. Even though it was in G star star, I just wrote what that isomorphism is. Okay? So now I can just take the commutator. So this is just the commutator of sigma df dxi alpha xi and maybe df1. I should say df1 here. So here df2 dxj xj. And now I expand by linearity. I end up with sigma df1 dxi df2 dxj. And the commutator of xi and xj can be expressed as a linear combination of the xk's, all the x's, all right? So I end up with Cijk xk, where the Cijk are just the structural constants of this Lie algebra. In other words, xi xj is equal to sigma k from 1 to n Cijk xk. Okay? So I obtained some explicit formula for this bracket, but now I have to use this to actually show that I got a Poisson bracket. So now, don't forget that we also have some evaluation. So we have to evaluate this at alpha. Okay, so let's do this last step. So then what is alpha evaluated at df1 alpha, df2 alpha? So now I have to evaluate alpha at all the xk's, right? So then it will simply be sigma, again, summation over all ijk between 1 and n, df1 dxi, df2 dxj, cijk, and then alpha xk. Okay, so this is an explicit formula for this. And now checking that we actually have these properties is not that hard. So let me explain. So first, let's check the property of skew symmetry. So we want to show that f2 f1 equals minus f1 f2. So can you explain using this last formula why this is true? So if I do f2 f1, I just get a similar summation. It's just that the role of I and j is changed. So I get like a summation df2. I mean, I can just switch the role of indices I, j, and k because it's totally symmetric. So I just can put like a dxj, and then I get df1 dxi, and then here I should put djik alpha xk. And now this is exactly the one I had before, except that instead of Cijk, now I have like a Cjik. And Cijk equals minus Cjik, because this one describes xi, xj as a linear combination of xk's, and this one describes minus xi, xj as a linear combination of xk's, because xj xi equals minus xi xj. Okay, all is good so far. Okay, so now this proves that skew symmetry holds. The Leibniz condition also is easy, and in fact, it's automatic from the formula up there. Okay, so what is the formula? So the formula, maybe I should rewrite this formula for the next step. So we set Wij alpha to be sigma Cijk. This is only summation on k from 1 to n times alpha xk. So this is a linear map, linear functional in alpha. Linear, okay? It's linear in alpha. Okay. Good to bear this in mind. It's a linear in alpha. Looks complicated, but it's just a linear map. Okay, so then F1, F2 in general is just sigma Wij alpha dF1 dxi dF2 dxj. Both at alpha. Okay. And now, for any expression like this, the Leibniz rule holds. So any expression, no matter what the Wij's are, so any expression in the above form satisfies the Leibniz condition. So why is that so? Why is this true? Well, let's look at F1, F2, F3. Well, I have the sigma Wij, and then I should do d dxi F1, F2, d F3 Cj. Okay. I mean, I just suppress all the alphas, and then I note that this is just, I mean, by the usual Leibniz rule from calculus, this is like d dxi F1, F2 plus F1 d dxi F2. And then I expand and I see that I can rearrange the terms in the form of two sums, the first being F1, F2, F3, the second being F2, F1, F3. Okay. So these guys go in here, these guys go in here. I basically didn't use any property of the Wij's. I just used the Leibniz rule for like from calculus in one variable. All is good so far? So we check Leibniz. The only thing that's left, which is a little bit harder to check, is the Jacobi identity. All right. So let's see how the Jacobi can be checked. So I will keep using this notation Wij because it will simplify my life. Okay. So for the Jacobi identity, let's take f, g, and h as three functions, and let's write f, g, h. So using the general formula with the Wij's, I should write sigma Wij of alpha. Okay, maybe I just keep the alpha here. Everything has an alpha. But maybe, okay, maybe I can suppress alpha. That doesn't hurt. Then I should do d if. So here I also abbreviate my notation to avoid complicated partials. So d dxi, I will write instead di, and therefore, instead of df dxi, I write dif. Okay, and then I should write dj of the Poisson bracket of G and H. Okay, so what is that Poisson bracket? It depends on some indices K and L. I have to do some WKL, and then dkg dlh. Okay? Is it clear? I'm just doing calculus. All right? And now I can just, again, use the Leibniz rule to expand. So here I end up with sigma. I mean, there's like so many indices here, A, J, K, L. They're all varying arbitrarily. Okay. So I get Wij. First, I could apply the partial. So I get this partial J, WKL, and then I end up with this DKG. Well, I mean, there's a DIF. Maybe I keep it. DIF, DKG, DLH. Okay, so this is how it is. Plus another summation that involves applying this partial J to the other two. So this would be like Wij, WKL, and then I get DIF, and then well, I should do the DJ of the first or the second, so I could do like DJK of G, DH, LH, sorry. Or I could do D KG DJ LH. Okay. Are we following? Is it clear? Are you following? Okay. So now what's going to happen to all these terms? There's too many terms here. So like there's like basically it's three sums. Like I merged two sums, but there's actually three sums. But let's look at another term. So let's look at in the Jacobi, maybe I have like a GHF, and we also have the HFG. So let's write that guy, HFG, and compare. So by the same technique, so now I could use the indices Wij, but it's smarter to start with indices LK than IJ. Okay, so I write this as sigma WLK Wij. I mean, this will count as the first, or I would say this is like the last term here. Okay. But this time I will have like DLH. Sorry. So I have to differentiate this with respect to L because L came the first index here. Okay, so I do DLH, D K I yeah, DKI F DJH plus DI F D K J H G. Did I miss a G? Or this is actually G. Sorry, this is not an H. This is a G because the second one is like F and G. Okay, plus a third term that corresponds to the first summation, which is this one. Okay, the one that takes the derivative of the W guy. Okay, I'll deal with that term later, but these two terms that are analogous to the two terms above. Let's see what happens. So here I have like a LKIJ. The correspondence seems to be IJKL. It's just that the indices are in the opposite order, which is good because now WLK we know is minus WKL. This is because of the skew symmetry of the bracket. Okay. And then the other terms, how do they compare? So I have this partial JKG, partial LH. So I have partial KJ, but partial KJ and JK are the same thing. And I have the partial IF. Okay. So in other words, this term cancels with this term because the signs here are different. WIJ, WKL, WLK, WIJ, which has opposite sign. Okay. So I could say that these guys cancel. These two other guys don't cancel, but they really shouldn't, because this Jacobi identity has 3 terms. So it's not conceivable that this one should cancel with the other thing in the Jacobi, which is the GHF. And same with this guy. This guy should also cancel with the GHF somewhere, okay? And they do, just like this one, all right? So all that's left is one summation from each of these Jacobi terms. This guy and the analogous one in this guy and the other one, okay? So if we write them, and now we look at the coefficient of a certain partial in f, g, and h. So maybe we should look at the partial that showed up here, DIF, DKG, DLH, okay? So after the cancellations, so what we obtain is that FGH plus GHF plus HFG. So it's a bunch of terms, and I just, well, I mean, I have to sort them according to the partial they're multiplied. I'll take this as the sort of identifier. So the coefficient of DIF, KG, DLH, and clearly the index that is missing is J. So there should be a summation on J, because all the indices were varying, right? And the only one that I'm not controlling here is the one that is J. So I get a bunch of partials in J. The partials, WJ of the, like, I'm sorry, partial J of the W's. So what am I getting here? I'm getting Wij partial J of WKL. Maybe I just, okay, I'll just continue here. I just write it again here. So I get Wij partial J WKL. And the next one, if I do the calculations right, and again, look at the coefficient of this guy, I will, trust me, you will end up with WKI, KJ, partial J, WLI, and the last one, WLJ, partial J, WIK. All showing up as the coefficients of DIF, DKG, DLH. Okay? And now I have to show that this thing actually vanishes. All right? But now the point is that, remember, the Wij's were linear. So what is the partial J of WKL alpha? So this is partial J of this summation, which was CKLI alpha XI. And you can see that you're taking the derivative in the direction of CJ. The only one that survives is for the XJ, because otherwise you're taking the derivative in the direction orthogonal to the direction that's the function is varying. Okay? So when you do this differentiation, you end up with sigma CKLJ actually, there's just one term. No, because there's only one term here. I mean, I mean, here, the only thing that's varying is I. And as I said, there's only one term that survives. So this is CKLJ. Okay? The derivative of a linear map in one direction should be a number. Okay? It's like, you know, you think about this map, like a map A1x1 plus ANXN. As a function of the xi's. The ai's are constant. So you do d dxj, you should get x aj. Okay, this is just calculus, right? All right, so now when we do this, now what happens to these terms? Remember, we have the dj wkl, but we have the wij as well. So thus, FGH plus blah, blah, blah for this Jacobi, it is equal to like a double sigma Wij CKLJ WKJ CLIJ and WLJ CIKJ. The summation on J. And this is basically, so as I was doing the calculation before class, you basically see the Jacobi identity for the Lie algebra. So if I can write out that formula, that will be great. So why is it, okay, so why is it the Jacobi for the Lie algebra? Because if you think about so what are the coefficients? So what is this Wij alpha CKLJ? So this is sigma what's the best way to see this? So if you fix the index J, yeah, so this is okay, so this is the coefficient of some xj, but then so okay, so maybe we should just write out Wij. So Wij alpha is sigma Cij alpha xi Cijk. Now I have to make sure that I again don't mess up the indices. So Cij just copying from up there. All right, so maybe I should do maybe some index u alpha xu, okay? Yeah. And now if I multiply this by this CKLJ, okay? So this CKLJ, so if I do the summation over the xj, so basically I should end up with something like xu, xk, xl sort of thing, and then basically like the summation propagates over the tree, and I should get 0. Okay, so maybe I should complete this loose point in the slide. So I mean, I will complete this later on, and I'll post the slide. So the right-hand side vanishes because of the Jacobi in G. Okay. All right. So there's this last bit we have to just expand and see. Okay. Which I did in my calculations, but I do not remember. So these things, this is really one of those, like, this is just by computations, you can see these hold. But I mean, this is just like, in some sense, not difficult, but the computations can be confusing. Okay. Okay, so now what is the conclusion right now? So we got this Poisson structure on the dual of the Lie algebra, and then in some sense we want to get hold of the Poisson structures on the corresponding Lie group to G. Okay, so maybe maybe I can now define the notion of a Poisson-Lie group. Okay, so here's the definition. So Poisson-Lie group is just a Lie group. So remember, we talk about matrix Lie groups mostly in this course. So you can imagine that the local charts are coming from local charts in GLNC, basically from the Lie algebra. I mean, we know all of this, okay? And therefore, we can talk about, we can look at like open domains on this Lie group as a manifold, and everything about this Poisson structure locally, we could just pass to some open domain in some Rn, in other words, okay? All right, so now, so the Poisson Lie group, therefore, is a Lie group that's equipped with the Poisson bracket. On C infinity G. Okay? Such that the Poisson structure is compatible with the group multiplication. So in other words, the multiplication, the multiplication map of the group is a Poisson map. So here on the product, remember from the last lecture that on the product of two domains with Poisson structures, we have another Poisson structure. That was basically defined in one of the early examples. So if U and V are domains with Poisson brackets, then we have this sort of a bracket with respect to each coordinate, the sum of the brackets with respect to each coordinate that will define another Poisson bracket on U cross V, on the Cartesian product of U and V. Okay, so now we can do the same thing for G cross G. So this is equipped with the Poisson bracket of the Cartesian product. Okay, and now the condition for making G a Poisson-Lie group is that this map mu, the pullback of the Poisson bracket here is the Poisson bracket that we get here by this Cartesian. So mu is just a multiplication sum. So mu of AB is A times B. Okay, all is good so far? And then we can talk about a homomorphism of Poisson-Lie groups. Okay, so homomorphism. Poisson-Lie groups is just a Lie group homomorphism, which is also Poisson map. Okay. So you might ask how the Poisson structure interacts with the inversion of the group. And in fact, the inversion map is almost never a Poisson map because it actually reverses the bracket. So here is a remark. I'm not going to prove this, but it can be proved. It's not so difficult. So here's the remark. If iota from G to G is the map iota of G equals G inverse, then if you pull back the Poisson bracket according to iota, you end up with the opposite bracket. Okay. Note that minus a Poisson bracket is also a Poisson bracket. Just like minus a Lie bracket is also a Lie bracket. All the conditions are linear, and therefore you can change the sign. Okay. Any questions so far? All is good? Okay, so now, just like we attached Lie algebras to Lie groups, we can now associate a structure slightly more decorated than a Lie algebra structure to a Poisson-Lie group. Okay, so this is somehow our way of controlling Poisson-Lie groups by something Lie algebra-like. Of course, the Poisson-Lie group has a Lie algebra, but this Poisson structure allows you to do more. Okay, now it allows you to add more structure. So let's see how this works. This leads to another important structure, which is called the Lie bialgebra. Okay, so here is what we want to do. Okay, so maybe I should say the Lie bialgebra of a Poisson-Lie group. Okay. Are we going too fast, or is it at good pace? Yeah, all is good. Okay. All right. Tianyi, all's good. All right, so here's what we do. Suppose G is a Poisson-Lie group. And as usual, fracture G is the Lie algebra of G. So now we would like to give a Lie algebra structure to the dual of G. Note that the dual of G, G star, a priori doesn't have a Lie algebra structure. It was G that was a Lie algebra, so the dual doesn't have. But, well, you could say that the Lie bracket, it's a bilinear map in this direction. And now we would like to go in the other direction. When we dualize, we should be able to go in the other direction. Okay, but what is the right object to put here for this to make sense? Because we can dualize linear maps, but this is a bilinear map. So here, kind of fun question would be, what is the dual of a bilinear map? Okay, and we have kind of discussed this. What's the dual of the bilinear map? Yeah. I mean, the first thing is to think about the bilinear map as a linear map.
So you use the tensor product and then you get a sort of...
That's right. So the right way to do this is to think about the bilinear map as a linear map from the tensor product G tensor G, and now we can dualize to a map from G star to G star tensor G star. Okay, so the product, the Lie bracket of G turns into some map in kind of the opposite direction. I'll be more precise about what this tensor means whenever we need more. But at the moment, just to show you that by dualizing the product, we do not get a product. We do not get a Lie bracket. But then we have to come up with another Lie bracket on the dual of G. So here's what we do. Okay. So take, so 4. So okay, maybe I should say motivate. So maybe the goal is to equip G star with the Lie bracket. Okay, so what we do is, so given, say, I'll call them C1 and C2, just some elements of G star. Okay. So we pick functions on capital G whose partial derivatives, whose derivatives are these guys. So we choose some F1 and F2 in G star, I'm sorry, in C infinity of capital G. Such that the derivative the identity element of capital G is C1, and the derivative and the identity of F2, C2. Okay? So remember, we had this discussion that in fact, the Lie algebra really is the tangent space at the identity element. This was because like it was obtained by all the vectors that were tangent to the curves passing through the identity element, okay? And therefore, the derivative of a function on G should have values in the dual of this G, which is G star, okay? So now I'm doing the opposite. Now I'm taking the derivative and I want to give a function whose derivative is this. This is like, something like, you have the derivative of one variable function. You want to give the function with that derivative. What do? You kind of integrate. Okay, so the answer is not unique, but it is always possible. Okay, I'm not putting any severe restrictions on the functions. It's just the functions are smooth. Okay, is it believable? Everybody happy with that? So note, maybe I should say that the choice of oops. F1 and F2 is not unique. Okay, so there is some redundancy. You have to make sure if you want to define the bracket of C1 and C2, it is well defined. So what do we do though? Well, we had this Poisson structure on capital G. Okay, that was by the assumption. Okay, so now we set. Well, we first compute the Poisson bracket of these two. This is now a new function on capital G. And now we differentiate this function and evaluate at the identity. So this is another element in G star. Okay. So now, so here, the remark is that if we know that this construction is independent of the choice of F1 and F2, then it's automatic that we got a Poisson bracket. Because all the conditions will be inherited from the Poisson bracket on capital G. Okay? Because this is not so difficult. So if we know that maybe I should write here, we set C1, C2 defined to be this. So if we know that this C1, C2 is independent of the choice of F1 and F2, then verifying that we have a Lie bracket is straightforward. And the fact that it's independent of the choice of the functions is that really the formula for a Poisson bracket depends on the first order partials. I mean, we have to do another D here, so you have to really show that that doesn't destroy things. But really, the Poisson bracket of F1 and F2 is just like D. So I mean, this is like D XCI F1 D XCJ F2. So this only depends on the order 1 partials. Okay, and we are assuming that they are given. Okay. Okay, so in this fashion, we defined a new Lie bracket on G star. I mean, just G star didn't have a Lie bracket, we just got a Lie bracket, right? And this extra structure is the sort of infinitesimal version of the Poisson structure on the Lie group. Okay, so the sort of correspondences you've seen between Lie algebras and Lie groups now extend in some fashion to correspondences between Poisson-Lie groups and these Lie bialgebras. Okay, so but what is a Lie bialgebra really? So here's the definition. Let G be a Lie algebra. A Lie bialgebra structure, Lie bialgebra structure on G is a Lie bracket on G star denoted as. So I'll use this delta star. That's a map, the bilinear map from on G star with values in G star, okay, from G star cross G star with values in G star, or equivalently, the linear map on this tensor product such that so the dual map, and I'll be more precise about some of the things that I have not defined here, okay? So the dual should go from G to this tensor product satisfies, and it satisfies the following conditions. I mean, just one condition to be precise, and that is the following: delta of the bracket. So somehow this delta, which comes from the bracket of G star, should interact with the bracket of G. Somehow they cannot be independent of each other. They should talk to each other in the following language, in the language of cocycles, which is this. So what does it really say? What is it really saying? Okay. So first, let me say a few words about G tensor G. So does anyone want to define G tensor G? How many are familiar with tensor products of vector spaces here? Okay, everybody. So okay, so then at least one of you should tell me what G tensor G means as a vector space. What's your way of thinking about it? So here's the question: how do you think what's your favorite way of thinking about it? I mean, this, yeah.
You take like a basis of G, and then you get together basis element of G with basis element of G, and any combination of like sum of.
That's right. So you want to think about this as you take a basis of G, like x1, say to xn of G, then G tensor G is a vector space. It's also over R, real vector space, same field as G, with basis consisting of symbols xi tensor xj for all choices of I and j between 1 and n. Okay, so in particular, if say we have just two vectors. I mean, for instance, maybe I just do some small example, for instance. So if n is 2, so the basis for G would be x1 and x2. And the basis of G, tensor G, it consists of the four vectors x1, 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 x2, x2, x1, and x2, x2. So every vector in here is a linear combination of these four guys. Okay? All is good so far?
Algebra is a set or a set function.
Well, the bialgebra, so well, G is a Lie algebra, and the Lie bialgebra structure means, well, on G, we choose a certain Lie bracket. I mean, well, we fix G, and then we choose a Lie bracket on G star. So the dual of this bracket will be a map in the opposite direction, going from G to G tensor G. Okay, in other words, you could say a Lie bialgebra is a pair of a Lie algebra and some delta going from G to G tensor G, such that the dual of delta is a Lie bracket and there is a cocycle relation. Okay. So now let's see what this cocycle relation means. That also requires a bit of interpretation. So on the left-hand side, so what do I have on the left-hand side? I apply delta to some element of the Lie algebra G because I'm taking the bracket of two things in G. Okay. So this is in G tensor G. Okay. This is some vector which is a, in a linear combination of those like xi tensor xj's. What about this? What does this mean? Well, delta y is in G tensor G. How can I take the bracket of this guy with something in G? Does it even make sense? So I have to define it. It doesn't make sense a priori. Okay. So this is only in G. But what do I mean by this? By this, I mean, so here's some convention. So for x in G and y and, okay, maybe I should say for x, y, and z in G, x, y tensor z, I define it by Leibniz rule. This is like x, y tensor z plus y tensor xz. So now this is in G. So this tensor is in G tensor G, and this is in G. So this thing is in G tensor G, and now I'm adding these two. Okay. So here you have to make sure that you're adding in a bilinear way. In other words, you're not mixing up the concept with direct sums. So what is this? Is this true or false? If the xi's form a basis. Is this true or false?
False.
It's false. And why is that? What do I have on the right-hand side?
Left-hand side plus xi tensor xj and xj tensor xi.
That's right. So I have to expand in a bilinear way. I mean, xi tensor xi, xj tensor xj, well, those are for sure there. But I also have xi tensor xj and xj tensor xi. So these two guys are not present on the left-hand side. Okay. All right. Everybody is on the same page with these tensors. Is it clear? Okay. And now we can extend this convention to more tensors. So it's like a more general convention. that if x and x1 up to xn are in G, then we can take the bracket of x with the n-fold tensor product of these guys. Now, this is an element in G tensor G n times. I could write this as G upper n, tensor upper n, which is G tensor G n-fold. Okay, so what I do is I just take the commutator of each x with the corresponding xi and put it in the ith position and then add. Okay, so this will be x1 plus x1. Okay, here this is a little bit unclear, so it's x comma x1. Then I do x comma x2. And so on and so forth until I get to the last. Okay, so the right-hand side again is an element of this G tensor for n tensor n, n-fold tensor. Okay, and this relation here, up here, it should be understood as such. Okay. We can start an example, but I wanted to put part of this example as an assignment question. So here is an example. So we can start this example. So let's take G to be the Lie algebra SL2C. With the usual basis H, E, and F. Where HE is 2E, HF is minus 2F, and EF H. You remember this? Okay. So then here's a Poisson structure on this algebra. So I mean, I have to define the bracket on G star, but rather than that, doing that, I define the delta, which is the sort of co-bracket going from G to G tensor G. So we define. So I have to give a linear map in this way. And to give this linear map, it's enough to give its values on a basis. So I define delta of H, delta of E, and delta of F. So I set delta of H to be 0, delta of E to be H tensor E minus E tensor H, and delta of F to be H tensor F minus F tensor H. Okay. So now we can try to see what really this delta star was, what Lie bracket it was. Okay. So, I mean, to see delta star, the smartest choice would be to take the dual basis. Okay, so you take the dual basis H star, E star, F star. All right. So now let's do some computations. So what is delta star of so delta star really goes from G star tensor G star, but it's supposed to be a Lie bracket. So I could just write it as H star H star. Oh, maybe okay, maybe I should write okay. We just write it like this. Maybe I could write H star H star. This is delta star of H star H star. Okay, what should it be? So I should evaluate this at different elements of G to see what element of G star I got. So evaluation at H. So maybe I should write it like this. So delta star of H star at H. By the definition of the dual map, this is H star evaluated at delta of H. But delta of H is just 0. Okay, so this is just 0. Okay. What about delta star of this guy at E? So this is H star delta E. But what is delta E? Well, delta E is like HE minus EH. We have it up there. So we got H star HE minus EH. But now again, you know, I've chosen a dual basis, right? So if I evaluate, I get H star of H multiplied by H star of E, but H star of E is 0. Okay, so again, I end up with 0. And well, delta star H star F is 0 for the same reason, which is not surprising because this basically says H star, the bracket should be 0. But it becomes more interesting if we wanted to do something else. Maybe we do delta star of H star E star. This really should be the bracket of H star and E star. Okay, so this is going to be, okay, now what is its value? I'll just do its value at E and leave the rest to you in some assignment question. So this is going to be H star E star of delta E, which is HE minus EH. And now the HE guy will be non-zero because it's H star of H. So this is going to give me H star H E star E minus H star E E star H. But obviously this is 0 because of the dual basis property, whereas this one is 1 times 1. Okay. And now you can continue and see, in fact, what linear combination of H star, E star, and F star we get here. And I leave it to you to do the calculation. Okay, so next time I'll talk about a general way of constructing Lie bialgebra structures, and then connections with braid groups and so on. And then hopefully if there's extra time, I talk a little bit about quantum groups as well. But how many, we have 2 more lectures, right? Okay, so yeah, next time, hopefully we will finish this. So next time I'll talk about the classical Yang-Baxter equation. And then this will be motivation for the quantum Yang-Baxter equation. How many of you are familiar with the classical Yang-Baxter equation? In what context? Have you seen this?
Seen the quantum Young-Baxter equations, and then
Okay, so you've done the quantum version and
but
not.
not.
Okay, so now this is the classical story. I mean, as much as one can call Lie bialgebras classical. Okay, we can stop now, and next time we'll talk about the classical Young-Baxter equation.